The title is, this is the first talk, because there will be a second talk after this. And the title is Existence and Stability of Stationary Points in Two-Strain Dengue Model.
Thanks a lot. So thank you for possibility of talking here. So maybe I'll start with the question that arose just before seminar. Should I speak in English or in Polish?
English,
so there was a question about the origin of the word, which is in English is rather pronunciation like dengue. And there are some theories about this origin. So maybe it's borrowed from a Swahili phrase, ka dinga pepo, meaning cramp-like seizure caused by an evil spirit. And this phrase was likely borrowed into Spanish and then into English, where it evolved to dengue. Another word proposed a link to the word dengue, referring to the stiff, uncoordinated gait of people with the illness. So, to say, but it's not coming from the name of. So I'm going to focus on the paper that has been published actually in April, so now appeared, and it was joint work with Marcin Choiński and Urszula. So first, I will talk a few words about the illness that we are going to talk about the model of this illness. So dengue is one of illness that is common in tropical and subtropical zones, and there is more and more infections. So nearly 400 million per year, actually. And this is one of mosquito caused infection. So it's vector. If you are familiar with some epidemiology, it's vector caused disease, and due to change of climate, this illness is spreading to new areas. So it also reported some cases even in Europe, and last year we could hear about some cases of dengue in Europe actually. So you have these cases in France, in Russia, in Portugal, and also some deadly cases like 2024 in Bangladesh. Okay, so there are some maps of dengue fever risk areas. So you can see that it's mainly like south.
In Brazil, you told
yes,
Argentina, but Brazil.
Yeah, there is also there is more. So you can see there's more and more. Okay, so let's look closely at some characteristics of this infection. So it's transmitted by bites of infected female mosquitoes, and there are mainly two species that are involved. So we have Aedes aegypti, czyli egipski komar, and Aedes albopictus. So mosquitoes can be infected when they bite infected humans, so have this two-way transmission. So humans, after getting infected, they are ill, but mosquitoes are not infected in this way that this causes anything about this. They just carry this virus. So we also are going to model some phenomena that is possibility of transmission of the virus from female mosquitoes to eggs. Okay, so we are going to capture this possibility that it's not only from that this virus can be introduced to the system of mosquito, not only through bites human who are infected already, but also there is some possibility that they are burned, that mosquitoes are burned with this strain. So we are talking about strains. So there are 4 different stereotypes, so genetic stereotypes of this dengue. There's 4 of them. So in previous literature you could see the information about 5, but lately it was discovered that actually there are 4. So this was some misunderstanding about this number. So there are 4 different. And what is interesting about this illness? If human individual is infected by some strain of this dengue virus, then this infection is not very severe. It's kind of mild, and this individual can gain some immunity.
Strain po angielsku to co jest po polsku?
Szczep. Czyli mówimy o takich genetycznych stereotypach. Szczepach.
But is the same stereotype or different thing?
A little different.
So for instance, how many more strains there are stereotypes or?
We have 4 stereotypes, and they also people distinguish sometimes between strains that are I don't know, Asian or something like that, or American, something like that. But from the point of view of the model, it was shown that it's important to have to distinguish between 2. Okay.
I see.
Okay. So I was talking about this immunity that you can have after recovering from the first infection, right? But then it is possible that you are going to be infected the second time with different strain, and this infection by different strain it can be dangerous. Because this is more severe course of dengue.
So this is infection after recovery. It's
yes,
not
after
during.
recovery.
It's not you're very unlucky and you get bitten by 2 mosquitoes at the same time. You recover and then your immune system has an unwise reaction. Okay.
And this is probably because there are such differences if this some genetical differences in these stereotypes, these strains, that if you are recovered after getting infected by one strain, you have some antibodies and so on, but if you are infected with different strain, that your immune system doesn't recognize that this is the same illness actually. it is treated like completely different, or that there is no illness, right? Doesn't see the difference, and this is why the immune system does not defend. Okay, so that's why it's so dangerous. So yeah. So there are clinical evidence for this, and this is why, which we are not going to talk about this in this model, but I want to mention that because of that, the vaccination becomes problematical. Because if you are vaccinated, you are vaccinated with respect to some strain, usually, right? So then you, especially if you are coming to this kind of country where the dengue fever is quite high risk, right? So you are vaccinated, and then you go there, and then it's likely that you are getting infected with another strain, that you are going to be very ill.
What happens if you get a third strain? Because I assume that some people can recover from getting the second strain. It's not 100% deadly. So what happens if you get a third strain?
Yeah. It's probably the same, but with respect to to our model, it's like you have one disease and the other disease. So
one strain is okay, two strains is bad.
Is bad.
But can you vaccinate for all the strains?
There is no such vaccination.
I assume the virus mutates too quickly.
There is no some vaccination.
So the best thing will be to anti-vaccinate.
There are some vaccinations, there are some vaccines, but they are not so effective. So also like WHO is very careful about advising to vaccinate. Yeah, so with this secondary infection with different strain, you can have some serious phenomena like dengue, hemorrhagic fever, and dengue shock syndrome, and then you require hospitalization. So this hospitalized also are going to include. So I was mentioned that you can be infected by the bite of the infected mosquito, right? Female mosquito. So this is due to the life cycle of mosquitoes. So you have different stages for pre-adult mosquitoes, right? So you have eggs that can carry virus. You have larvae, then you have pupa, yes, and we are going to call of them larva stage, okay? So don't distinguish between these three. And then you have these adults, you have male and female, and female mosquitoes, at some point, they are seeking for blood, for human blood, because it's essential for them to lay eggs. Okay, and that's why it's
Vaccinate all mosquitoes. That was supposed to be a joke. I'm sorry.
No, not vaccination. It's also something that I'm not going to talk about, but it's kind of interesting. There did some works to introduce into mosquitoes some, I'm not sure what was it. Whether it was virus or bacteria or something like that, but it was something that doesn't harm mosquito in the sense that they are dying, but prevents them from being infectious. But it's hard to, it's hard to make this work. Okay, so now we are coming to this model, and in this model we are going to have some variables. There's a lot of them actually. So number capital N is actually not a variable, it's a constant, it's a total number of humans. We are not assuming that people are dying due to this illness, and this number is constant. So then you have this class of susceptible. So this is the class of people that can be infected. Okay, then you have class I, which denotes primary infected with strain correspondingly first or second, right? So we are going to model two strains, and it can have this I can have index 1 or 2. Okay, and then you have individuals who are recovered after getting infected with this strain, and then you have people which are susceptible to another strain after recovering from one infection. Okay, so S1 means those that are immune to strain 1. But they can be infected with strain 2, and so on. And then you have these two indexes. You have these classes of individuals who are secondary infected, also hospitalized class, and individuals recovered from the second recovered from the second. Okay, so this was about humans. This is about mosquitoes. So this is our vector. And as we said, we have those larval stages, and we distinguish between susceptible larvae and those who heritage strain. Okay, strain 1 or strain 2. So we have this index I. And then you have adults, susceptible adults, mosquitoes. We have more formal classes actually. So we have exposed adult, which means that there are mosquitoes, female mosquitoes, which already carry the virus, but this virus needs some time to be dangerous. Okay. So this is this exposed class, and then the last two are infectious.
So these are two not intersecting, EI and VI.
Sorry?
So these are not two disjoint groups?
Yes. All of them you are going to have in equations. I just wanted to say that these are like human variables and these are like mosquitoes.
I mean that exposed adult does not count infections?
No, these are disjoint. These are disjoint. Yes, disjoint. So we need some incubation period for the virus. Okay, that's why you have this exposed.
So can E1 and E2 be are also disjoint, or can they intersect?
Yes.
Can we have mosquitoes carrying two strains?
No, we do not model this.
Hopefully not.
No, we do not. They are connected to say that they are.
Perhaps that again wouldn't matter, because if they carry a strain that you did not encounter, this is still your second strain, so it doesn't matter. If they carry a strain you already had, it's okay, it doesn't matter.
Okay, so then we have some diagrams. So, okay, so this is upper part of this first diagram that shows you the flow, right, of the infection. So you have these classes which are green classes, which are safe, right? So they are susceptible or recovered and so on. So they are not infectious, right? Red one are infectious, so we have I1 and I2 here, okay? And what is nonlinear in our equation is going to be some nonlinear terms. So there are those two transmission terms, okay? And then you have some parameters that correspond to natural death and to recovery or losing immunity, for example, right? So then you have this upper part, and then you have lower part of this diagram. So you have secondary infected classes here. So with two indexes 1, 2, and 1. And then from this you can go to hospitalized class, and then you can recover.
What are the Greek letters there? Alpha, gamma, delta?
These are parameters.
Some numbers.
So yes, some numbers. Yes, some numbers. So they are taken from some studies, from some experiments, and from some medical studies, and so on. So they are estimated usually. If you are going to make some simulations, then they are useful. And we are I'm going to show you the table.
Wait, delta is one constant.
Delta is delta is constant. Delta is death rate. Parameter.
Death rate should doesn't depend on where in the diagram you are. Because
no, doesn't depend. We assume that this is the same because it's natural death.
That's just okay. Because
we don't model the situations where people,
natural death is being hit by car.
By car.
So this is there's no correlation.
Yeah. So if you think about probabilities, it's pretty much the same. Doesn't matter which class one, right?
Sure.
Okay. And so this is the first part.
So where is the death because of the illness?
There is no death because of the illness in our model. It could be serious infection. You can go to hospitalized class, but we do not model death through the illness.
I guess it's small percentage here, so it doesn't affect.
And then we are going. Our model is like short term.
Okay.
No, do not model this. Okay, so the second diagram corresponds to mosquito classes, and then you have this larva class, which is susceptible class. So this is why it's green, and then you have L1 and L2, which are red because they carry virus. First strain or the second strain. This is adult susceptible class of mosquitoes, and then you have those exposed and infectious here. So here you can see this parameter height, which is responsible for vertical transmission.
I assume that the death now corresponds to the letter D.
Yes, death now corresponds to letter D, and birth corresponds to letter B. Okay, so here it's right, and then so
the death rate for adult to larvae, the death rate is constant in mosquitoes.
Yes, we assume that this is the same. Also, doesn't matter whether it's this class or this class. We could take different numbers. Anyway, still we have so many parameters that we are going to see that with respect to looking for stationary points and some useful characteristic of the stationary points. there are too many parameters actually, and there are some constraints that are,
Already.
yeah, already with this, yeah. So, okay, so you have these terms B here, which are transmission terms, and they are written here. So they correspond to the infected classes of humans. So infected, primary infected, and also secondary infected, right? I'm going to have those terms here. Okay. Yeah. So this is some kinds of already. And we are going to see this in equations. And here are first part of the equation. So there are equations for humans. The next slide is going to be for mosquitoes. So what is important here? You can see those linear steps here, right? And then the other are linear. So this is the system of ODEs. With a lot of parameters here. Yeah, so you can see that they have to go out from susceptible class to come to infectious class, yeah? And also with secondary infections that are going to escape like from S1, S2 classes to come to this A21 and 1-2 class. And these are mosquitoes equations. So these transmissions terms are a bit more complicated. You can see that it's also characteristic here. This is some way of modeling that in this transmission term, this is term which is like some mass action. So like, there is meeting between individuals from this class and this class, so that's why you take this product, but you divide something, and you divide here by the total number of humans. And also you divide by total numbers of humans in this mosquito transmissions term. Yeah? There are different models. In some models you divide here by humans, there by mosquito total number, but we are going to see, you could see actually from this diagram, we don't have constant number of mosquitoes, so it's difficult to divide by total number of mosquitoes. We have constant number of humans. But this is this is also some typical way of modeling the total number of human. So, as we said here, we have these more interesting transmission terms. And then we have those terms which are linear but corresponds to vertical transmission, if E. And there are some parameters. So, kappa, for example, is a parameter that corresponds to incubation period. And M is some parameters that corresponds to maturation, so from larval stage to adult stage. Okay. Okay. And D, as we said, is matter. Yeah. So here we have those parameters. So what is going to be important? These are parameters beta with index 1 or 2, and this is transmission rate of this virus. So actually, it's like transmission rate times probability of bites, right? So bites. This the in human. And gamma is corresponding to recovery, then you have loss of immunity. First, then you have those.
Is there some empiric idea why beta 1 and beta 2 should be different? So from like simple biology that I know, it's like if the virus is in mosquito 1, strain 1 is in virus 1 and strain 2 is in mosquito 2, if mosquito 1 bites one person, mosquito 2 bites the second person, then the transmission should not depend on the strain, but it does, I assume.
It somehow it does. I mean, from our point of view, like mathematical point of view, it's more interesting to have different class, because then we have some interesting phenomena that do not rise if you have the equality between all of these betas. Then there are also some studies that show that some strains can have different transmission rate than others.
Perhaps it's.
There are some, you know, and if you are going to take some of these beta numbers to show something numerically, so then we took this from literature, and they are different.
Okay.
They are different. There are also not so many, but I've seen also some models like this that you know that they assume that one strain prefers the other in the way that it's like 4 times more probable to be infected with this one and to get sick after that.
Okay.
Okay, so here we have these beta parameters, and here we have these beta tilde parameters that corresponds to transmission rate the other way. Yeah, and so we have 4 different betas. Personally, 4 different. Okay. Okay, so now we come to this main issue, which is about stationary state. Okay, so you distinguish in epidemiology. You distinguish between states that correspond to situation where there is no infection, and they are called disease-free equilibria, and the situation where there is infection, and then they are endemic. Okay, so first we are looking for this disease-free stationary point, which means that there is no infection. So you take V1, V2 equal to 0, and then you get something. So we can find trivial stationary point, and this is the situation where all humans are in susceptible class, right? So S is equal to N, where there is no mosquitoes at all, right? There is no mosquitoes at all. That's why there is no mosquitoes in U class or either in L class, and this is trivial. This is trivial stationary point. And there is also more interesting non-trivial stationary point. So then you have susceptible class equal to N, this total number of human. Then you have U, which is not 0, which is some number. And then you have larvae, yeah, susceptible larvae, which is called D over M times this U star. Okay? So this state exists if you have special constraint. So you need this constraint to have this state. That you have involved here birth rate, death rate, all for mosquitoes, and there is also maturation rate here. Okay? So you need this to have this state. And then if you start with 0, then you have equality of those 2 stages, right? One comes, this non-trivial becomes trivial.
What is D here?
D is death rate for mosquitoes. Death rates for mosquitoes, birth rate is B for mosquitoes, and maturation rate for mosquitoes, like coming from larva to adults. Okay.
So somehow there are mosquitoes which carry the infection, and still more humans are infected. I didn't understand.
Yeah, this is typical in the epidemiology, and also in these models where you have host and vectors, that there exists disease-free state where you have all people which are not infected in susceptible class, where you have vector which is in corresponding susceptible class vector, and there is no illness.
Miracle.
No, it's not a miracle. This happens with the mortality rates of the mosquitoes is kind of high enough. On one hand, the mosquitoes do not die all out, because if they don't die all out, you are back to
there is not enough. You can say there is not enough mosquitoes
to spread the disease. But on the other hand, there are mosquitoes. And obviously, this is a stationary state, so this makes sense.
Okay, so as we could see from this, we don't say that U star is some special number, it's just any number. So actually there is infinitely many non-trivial disease-free equilibria for this model.
But this is only for very specific B and D.
Yes, if you don't have this specific B, M, and D, there is no this non-trivial state.
Okay.
No, so this is important. Okay. Then we come to some special number which is called R0, which is characteristic in epidemiology, which corresponds to describes by definition the number of new infections caused by comes from one infection. Okay, so how many new infections arise if you have one infected individual? But there are different ways to calculate this. So there are some mathematical ways to calculate this actually, and pretty much it's like that you split your classes into those that are connected with infection and those who are not connected with infection, right? So like you have this red classes and these green classes, and then you calculate some Jacobian matrices, and you look for special values of some product. This product is F times V of inverse of V. This is a characteristic number. You have those parameters involved here, so have this transmission, vertical transmission probability here, this P, and then we have this death rate, of course. This is recovery rate. So we can simplify some notation to this in short way. So you can see this is function that depends of the product of bi times tilde bi, yeah, and maximum of this. Okay, so now you can see that if you have different pitas, then you have different R0s, yeah? Okay, then we are going to say something about this trivial free equilibrium and stability. So we see that this is locally stable if you have this inequality. This is unstable if you have otherwise.
This is the same equality that was beforehand. If it's equality, then this allows the existence of the other.
Of the other. Yeah, exactly.
Yeah, sorry,
exactly. Yeah, exactly. Existence of this non-trivial. Yeah. So if you have this equality, then you cannot say what is stability of this trigger.
Mm-hmm.
So the first case corresponds to the fact that we don't have enough bursts.
When you don't have mosquitoes at all.
Yes.
Yeah. And this is actually pretty much always what you can say about. So this is how you see what are these polynomials that have coefficients responsible for this construct. No?
Okay.
And this is pretty much all what you can say from mathematical point of view. Interesting about this model, yeah, because for this non-trivial, this is free stationary point. You cannot say what is stability, and this is because you have zero eigenvalue. About other eigenvalues is okay; they are negative, but the one is zero. Okay.
And only is the most important equilibrium.
Yeah. And then we try to look what situation comes about endemic equilibrium, which are more interesting from the point of view of disease. So actually, you see that there is no unique endemic equilibrium. Yeah? So you can say this about this one-strain equilibrium, also about two-strain equilibrium, that they are not unique. So we see that there are some problematic issues about this model, and this is why we decided to make some modifications, right, to get rid of those not good qualities. Okay, so. Yeah. So let's see what kind of modification we can. So first, yeah.
But this system does it fit well with the empirical data, with the known data for the spread of the disease?
If you are asking about the other models, usually they are models where there is one strain, so they are spread, or if there are two strains, then there is no so many results first of all, and there is no this vertical transmission, for example. There is no so many classes in human equations, right? So.
I mean, there is some historical data, right, for the
parameters.
Yeah, for parameters, yeah, you can.
Not for parameters, but for actual data for how many were ill, how many recovered.
Yeah, there are some data for this. Yes, of course.
And your model does it can it fit with the data that is described?
We made some simulations about the model which we simplified, yeah, because we could prove something mathematically,
yeah,
and then we could see like how it looks like in simulations, okay?
I see.
But not about the main, because we couldn't say nothing so very interesting. Trivial disease is not so interesting from the point of view of speed of disease. Right?
It should be the most interesting. That's the question: can you eradicate the disease?
But you know, this is eradication made by this that there is no mosquitoes. So
No,
this
no,
is
that's
not
what I meant.
real. This is not real.
So E0 is impossible to get because you cannot get rid of mosquitoes. First of all, they will destroy the ecosystem. But if you could eradicate the disease without getting rid of the mosquito, that would be awesome. But unfortunately, ED is A, non-stable. B, that would be that's a problem.
Okay, so let's try to see something about this model that could allow us to make some modification. So if you are going to call this pre-adult classes by the sum of them by capital J, like juvenile, okay, class. And then this adult, sum of all those adults with capital A, then you could see the simple system of two equations. And then you can solve this system of two equations, of course, in terms of some initial data. And then you see that you have infinitely many degenerate stationary points of this form where A is equal to M over D times J. No? But you need this kind of constraint. So this is the same constraint that was necessary to have non-trivial disease-free equilibrium. Written in different form, but this is the same constraint. Okay. So you could draw also some phase portrait of this simple system. So we have this trajectories. This orange line is the line that trajectories are parallel to, and it corresponds to this A equal to minus J. Okay? And then you have this line which is attractive line for equilibria. So all comes to this line. All those parallel comes to this. Okay? This 0 part doesn't. Okay, so we made some observation. Okay, so that this existence of non-trivial this free requires this constraint, and then we have infinitely many degenerate stationary points. And if t goes to infinity, then total number of adult mosquitoes and total numbers of juvenile mosquitoes, they are approaching some constants, right? So we actually are going to assume that total number of adult mosquitoes is constant, and we are going to denote this by A star, and total number of juvenile mosquitoes constant, and this is J star. Okay. This is the first assumption that we make. And then you can see from equations that exposed class, can be estimated from above in this way, and you can find the solution, or not only solution but the upper bound for this solution in terms of U and RE. So if you assume that we have this constant number of adult and pre-adult mosquitoes, then you can estimate from above. So also exposed class can be estimated in such a way where M is like a sum of this AJ and J, A star and the J star. And if kappa, this incubation period, comes to infinity, then we can come to 0. So we can get rid of the exposed class. Okay? This is something. So this constant number, that is what we assume, that we don't have anymore this exposed class, and also as then we don't have already this maturation rate and so on, then B equal to B, right? So we say that this dynamic in mosquito population doesn't matter for us. Okay. So we have the same birth rate and temperature. And the result is this, that we have still the same Human equations, very small of them, but we eliminate some classes in mosquito population, so exposed class, larvae, and susceptible also, both susceptible later, but still we have this vertical transmission. Okay, we want to keep vertical transmission. Okay, so we have this transmission rates, right? This transmission terms, sorry, and in this transmission terms there is U class, right? There is a class of susceptible adults, but since we have total number of adults equal to A star, and this is constant, we can say that this U is equal to A minus V1 minus V2, and substitute here. Right? So we can also get rid of this susceptible class. And then we have this simplified model. Okay, so only two equations for mosquitoes here, which is much better than the other one, and it's much better with respect to existence and stability of stationary point, actually. So now we can say something about this. This is free. So there is something to say here. So from this you could see that this is trivial. No, this is not trivial. This is free. You could see this non-zero susceptible class in mosquitoes, but we eliminate this class, right? So that's why you don't see this constant adult mosquitoes here. But still, this is our non-trivial. This is free, and this is it's unique. Okay. So you have this basic reproduction number, which is here. Still, you have this product and maximum of this product of beta, and you have some convergence with this kappa, right, which is natural. And then we are going to define some numbers which corresponds to first strain and to the second strain. Okay. They are going to be important in our results. So for this non-trivial disease free, you can see that this is locally stable if R0 is less than 1. And this is quite a typical situation in epidemiological. You expect this, that if R0 is less than 1, then your disease free state is locally stable. Okay, so here we calculate this Jacobian, and we can see that it works as it should be. Okay, so now we come to endemic states. Okay. So first, we are going to find some one strain, endemic states. So there is no secondary infection here. So we assume that this class is with two indexes 1, 2, and 2, 1 are 0, right? But those primary infected individuals they are present, and you can calculate those numbers, and you can calculate V1. Okay, so we just assume that there is this first strain here, right? Then we can say also it's quite analogous about the second one. So we have this V1, right? And you can express this in terms of this R01. Yeah? So from this form, you can see that if R01 is greater than 1, then this state exists. Right? So this is necessary for existence of this state, that R0 is greater than 1. So these are non-zero coordinates, the other coordinates are 0. So like hospitalized or something. No. The cover of the second infection, there is no second infection. And what is interesting about stability of this state? So stability of this state the answer is positive, that the state is stable if you have this kind of condition satisfied. So you need that this number is less than 1. So we can see here in these big brackets we have 1 plus something which is positive if this one strain endemic state exists, right? And then you have this ratio. So we need that product of beta 2s is much smaller than product of beta 1s to have this less than 1. Okay, so this is the situation where you really need that one strain dominates the other. Yeah? There is this biological interpretation. Okay, and then we can also say that we can so as we said that this is this. And then we can also find, of course, the second strain equilibrium. So the situation becomes analogical. For this, we need this R02. Yeah? So this is about one strain. Yeah, so you can see that in situation where R01 and R02 are both greater than 1, you can have both states, but they cannot be stable at the same time. Okay, so now we come to the situation where we assume that we have the full illness, and we have secondary infected individuals also. Yeah? And we are trying to find. I should finish shortly. Yeah. This. Okay. So we have this. So we have this situation where we have this two-strain equilibrium. Okay. So we can effectively find something where, for example, we assume some symmetry. So now we assume symmetry, and we're looking for symmetric stationary state. Okay, two-strain symmetric stationary state. So we take A1 equal to A2 and so on. This is the result. And so we have those variables. You can see they are all functions of this V1. Okay. So now this V1 is the solution to polynomial, to some quadratic polynomial. Okay. And you have coefficients of this polynomial. Okay. And then actually you have also some technical condition which corresponds pretty much to the situation, the existence of solution to this polynomial. Also requires that you have that you have 2 times V1 less than A star. This is pretty much this condition, right? Because we assume that the total number of mosquitoes is A star. So we have this upper bound for V1 plus V2, right? Okay. So here we can see from the coefficients of this that again for existence of this state we need R0 greater than 1. Okay, and then there is unique positive, which is biologically reasonable solution of this equation, of this constraint addition. Okay, so this free term in this polynomial can be expressed in terms of R0 again. No? Now R01 is equal to R02 because we consider symmetric state. Okay. And yeah, this is our conclusion. And also it looks simple. It's not so simple, but it can be shown that this state is stable if it exists, right? So if R0 is greater than 1 and this kind of condition holds. So in this 2-strain symmetric case, you don't need any special assumption. You just have stability of this state. Okay. What's more, if R0 is less or equal to 1, there is no positive solutions of this system. Okay, so it excludes this possibility. Okay, so I'm going to talk about this pretty much time. Okay, so this is some remark that we need for existence we need R0 greater than 1, and then you have equality of these products of betas, right? So as we said, so then also you can have both one strain equilibria, right? What they are missing. So you can see some picture of which visualize the local stability regions here, right? So below this red line here, you have stability of this is free here, yeah? And then you have corresponding stability of first strain, of second strain, or both strain are not visualized. So it's only one strain and it's free. Okay. Okay, so I'm not going to talk about the simulations anymore. So actually one of our conclusions is that this vertical transmission actually does not affect much the stability or the infection, speed of infection or something like that. Okay, so it can be also seen. Okay, thank you.
Thank you. Questions?
Yes, so I wonder, can you try to recreate some historical data using your models? I mean that, for instance, if we know how many infections were in 2000, 2001, 2002, you try to fit it and to see that if your model will accurately predict what happened in 2003, 2004, something like this sort.
Yeah, it could be just, the problem is that if you have some data, usually you have data that, for example, if you have data corresponding to numbers of infected, there is problem which infections are covered by this data, because usually if you are infected with first strain, it cannot be seen in this data because you are not so seriously ill to go to the doctor, to go to the hospital, to be treated like you just take some medicines that you can just survive by yourself, and so that's the first problem. The other problem is that what kind of this transmission rate and so on, this data corresponding to mosquitoes you are taking, right? Because there are also different sources and there are some ranges of the parameters. You can take this one or this one and so on. Yeah, so you can fit. Yeah, you can try and fit, but the problem is whether it corresponds to this real situation. So it's problem.
You discussed stationary states, what about periodic?
Yeah, that's one of my questions.
No, we didn't look at periodic states.
You didn't discuss.
For example, if you, instead of taking A star as a constant, what if you assume AT is periodic? So like the population of mosquitoes changes periodically, which, if I remember, something would be very close to the reality. So can you prove again some stability if you assume that AT is periodic?
I don't think so.
Yeah.
I think it's not enough. I think the model is too big to get this. Yeah, these mosquito equations are of this particular kind that You could have something. You could have something about some, I don't know, some bounds for this, right?
Mm-hmm.
You could say something about this. Maybe you could say something about upper bound, lower bound, and so on solutions. Sub solution, super solution. Then you can say something.
Equilibrium, then you might change parameters and get Hopf bifurcation. Maybe it's periodic.
Yeah, it would be interesting, but maybe with not so many equations, yeah.
Yes.
Because I'm glad to see this whole bifurcation, but we don't have. I think we don't have this situation with so coexistence of the states to get this.
Okay. I have a question. So, in your model, you have a situation when so your first infection is typically mild, right?
Yes.
But after the second,
it can be severe. Yes.
So is this very important for your model? I mean, if you have a situation in which, say, first infection is more severe, but the second is less severe because
it can also be included in the model. It's just not a situation that corresponds to reality.
I see.
It's not.
But the other diseases might be.
With the other diseases, probably there is no such phenomena like for dengue that these strains and the situation that the second infection by different strain is serious.
So you have inverse correlation.
Yeah.
Okay, I think because we have some next lecture. Thank you.